In this lecture, we'll be discussing about dynamic linking and shared libraries. So in order to understand in this lecture, we'll be discussing about dynamic linking and shared libraries. So in order to understand dynamic linking, we need to know that when a program runs, apart from its own modules, it also needs to use certain system libraries as well. So when a program is running, we know that the program has its own modules, which is compiled and loaded. And apart from these modules that belongs to the program, it also needs to use certain system libraries which are a part of the system. So the system libraries are also required for the complete execution of a program. Alright, so keeping this in mind, we will try to understand what is dynamic linking and shared libraries. So in order to understand dynamic linking, first of all we will try to see what is static linking, and we will see why is static linking not efficient, and hence we'll be able to understand why we need dynamic linking and how dynamic linking works. Alright, so first of all let us see what is static linking. So in static linking, system language libraries are treated like any other object module and are combined by the loader into the binary program image. So as we just said, when a program runs, it needs to make use of the system libraries as well. So in static linking, what happens is these system libraries are treated like any other object module of the program and are combined along with the other modules of the program and are loaded into the binary program image. Okay, so to understand this, let me take a simple real life example. So imagine that you are living in a house with your family. So you are living in your house with your family members, and think that there are different rooms in that house. So there is one room for your parents, one room for you, one room for your brother, one room for your sister. So think that there are these 4 rooms in your house. Now, let us think of some common thing that we share in a house. Like for example, a refrigerator. Yes, a fridge is something that we share commonly in a house. So we have one fridge in a house that is kept somewhere in a common place in the house, and we all share that same fridge. You keep your food there, your brother or sister may use it for keeping their food as well, and so on. So that is something that is shared. So now let's think of another way. Let's say that instead of having one common fridge, you decide to have one fridge each for all of the rooms. Then what will happen? So you will have one fridge in your room for your purpose, one fridge in your parents' room, one fridge in your brother's room, one fridge in your sister's room. Now what happens if we do this? We are just simply wasting the space of our rooms, and we are spending unnecessary money for buying different refrigerators which could be shared by the entire household. So static linking is something like that. Think of the fridge that we talked about as the system libraries. So here each of the programs are going to have a copy of that system library along with their own modules. So it is just like having one fridge each for all of the rooms. So here, instead of using something that could be shared, instead of having one common thing, we are trying to have a copy of it in each and every programs. So this is what happens in static linking. And what is the disadvantage of this? You must have already guessed it. Each program on a system must include a copy of its language library, or at least the routines referenced by the program in the executable image. And what will this cause? This requirement wastes both disk space and main memory. So this is the main disadvantage. We are simply wasting the disk space and also the main memory by having a copy of the system language libraries for each of the programs. So this is what happens in static linking. So now you must be getting an idea of why we need dynamic linking. So let's see what is dynamic linking and how is it different from static linking. So in dynamic linking, it checks to see whether the needed routine is already in memory. If not, the routine is loaded into the memory. So in dynamic linking, instead of having the system libraries copies for each and every program, we are just having the system libraries reside wherever it is, and then just when the program needs to use that library, we will be loading it into the memory and we will be using it for that particular program. So first of all, it will check if that routine is already present in memory or not. If it is already there, well and good, we can just make use of it. And if it is not, then the routine will be loaded into memory. So unlike static linking, we are not going to have copies of these routines or libraries for each and every program, and we are not wasting our disk space and main memory. So this is the advantage of dynamic linking, and this is how it differs from static linking. Now the concept of dynamic linking is similar to that of dynamic loading, but here linking rather than loading is postponed until execution time. So in the previous lecture we have discussed about dynamic loading. So that also was something similar, if you can recall. So this concept of dynamic linking that we are studying now is also somehow similar to that of dynamic loading. But the difference is that here the dynamic linking rather than the loading, it is postponed until the execution time. So this is done during the execution time. So that is the difference that we see from dynamic loading. Alright, so now let us discuss a little more in detail about this dynamically linked libraries. So when we say dynamically linked libraries, you may be familiar with the DLL files. So DLL files are Windows way of implementing the dynamic linking. So you must have heard of DLL files, and sometimes when you may be running some programs, you may get some errors saying that the DLL file is missing. So DLL is nothing but it is Windows way of implementing this dynamic linking. Okay, so talking a little more about dynamic linked libraries, with dynamic linking, a stub is included in the image for each library routine reference. So with dynamic linking, we are using something called a stub, which is included in the image for each library routine reference. Now, what is a stub? A stub is a small piece of code that indicates how to locate the appropriate memory resident library routine, or how to load the library if the routine is not already present. So as we already said, in case of dynamic linking, the system libraries or routines that a program needs to use will be located from the place where it is present, and it will be loaded if it is not present in main memory, and it will be used whenever it is needed. But the question here is, how will the program be able to locate those system libraries or the routines? How will it know where it is present, and how will it be able to load it into the memory? So in order to achieve that, we are using this stub. So the stub is nothing but a small piece of code which helps in achieving this task. It will help in locating the appropriate memory resident library routine. That means it will find out where it is present, and it will also know how to load that library into the memory if the routine is not already present. So this is the work that is done by the stub. So when a stub is executed, it checks to see whether the needed routine is already in memory. So as we already said, the stub, what it will do, it will first check if the needed routine is already present in memory. If it is already there, then well and good, it will just find the address of that in the memory, that means in the main memory, and it will just make use of it. And if not, the program loads the routine into memory. So when the stub checks for that routine, and if it finds that that routine is not already present in memory, then it will locate where is that system library or routine present in the disk, and it will load that into the memory so that the program can make use of it. So either way, the stub replaces itself with the address of the routine and executes the routine. So either way means even if the routine is already present in memory, or even if it is not present in memory, what the stub will do, for example, if the routine is already present in memory, then the stub will replace itself with the address of that routine. That means whatever is the address of that routine that we need, that address will be written into the stub. And in case, let's say that that routine was not present in memory, then what will the stub do? The stub will help in locating that in the disk. When I say disk, know that it is a secondary memory. So from the secondary memory, that routine will be loaded into the main memory, and then that address will be written into the stub. So whether the routine is already there in memory, or even if it is not there, in both cases, the stub will be finding the address of that library, which is either present on main memory or which will be loaded to main memory. And then that address of that library will be written into the stub. So think that when the library is loaded, the address of that library gets written into the stub. So the stub now contains the address of the routine, and then it executes the routine. So what is the advantage of this? So the next time that particular code segment is reached, the library routine is executed directly incurring no cost for dynamic linking. So why do we say this? This is because the stub, as we said, has replaced itself with the memory address of the library that was needed. So the next time that code segment is reached during the course of its execution, the stub already has the address of that library within itself. So we don't need to make the stub search for it again. So hence the library routine is executed directly, incurring no extra cost for dynamic linking. So this is what happens, and this is how the stub helps us in locating the library that we need and for loading it and executing it in case of dynamic linking. So this is how dynamic linking works, and I hope you have understood why we need dynamic linking, how it is much better than static linking, and how it makes our computation more efficient by using this dynamic linking. So I hope this lecture was clear to you. Thank you for watching, and see you in the next one. In this lecture, we'll be discussing about the next topic in memory management in main memory, which is swapping. So swapping, as the name suggests, you must already know what swapping means. So swapping means we are just changing the location of two things from their respective locations to the opposite locations. So that is what we basically mean by swapping in real life. So let us see what do we mean by swapping in case of processes, in case of the memory management. Alright, so talking about swapping, the first thing we need to know is a process must be in memory to be executed. So this is something that we have been repeating again and again in this topic of memory management. So we know that a process must be in memory to be executed. In memory means it must be in the main memory to be executed. So this is something we know. A process, however, can be swapped temporarily out of memory to a backing store and then brought back into memory for continued execution. So during the course of execution of a particular process, it is possible that we swap out a process from memory to a backing store and then brought back to memory for continued execution. That means a process P1, let's say it is executing in main memory. So due to some reason, that process can be halted and it can be swapped out of main memory to a backing store. So backing store is like a temporary storage location for these processes when they are swapped out of the main memory. So a process can be swapped out of main memory and kept in a backing store, and later when that particular use case is over, then that process can be swapped back from the backing store into the main memory so that it can continue its execution. So this is something that happens in the course of execution in operating systems. Now just to get a clear idea of when can swapping happen, let us take an example. So in a multi-programming environment with a round-robin CPU scheduling algorithm, when a quantum expires, the memory manager will start to swap out the process that just finished and to swap another process into the memory space that has been freed. So when we have studied about the CPU scheduling algorithm, we have studied about this round-robin scheduling. So in round-robin scheduling, if you remember, we are having a certain time quantum for each of the processes for executing. Like for example, let's say that 10 milliseconds is the time quantum that is given. So each process which are waiting in queue to be executed will be allowed to execute for 10 milliseconds. So let's say that we are having three processes, P1, P2 and P3. So when they are executing, let's say that they start with process P1. So P1 is executing for 10 milliseconds, which is the time quantum. So after the time quantum expires, what happens? P1 has to be preempted and P2 has to be given the chance for executing for its time quantum of 10 milliseconds, and so on for process P3. And after P3 completes, again, according to the round-robin algorithm, P1 should again get the chance. So that is how it works in round-robin scheduling. Now, when, let's say, P1 is executing for its 10 milliseconds, and when P1 has to be preempted, what happens? So, P1 will be swapped out of the memory. So, P1, as we know, will be in main memory. Why? Because a process must be in memory to be executed. So, the P1 which is in main memory, after it completes its time quantum of 10 milliseconds, it will be swapped out, and where will it be kept? It will be kept in a backing store, and after that P2 will be given the chance to execute. So P2 will be given the chance, and P2 will execute for 10 milliseconds, and after that what happens? P2 will be swapped out. P2 will be swapped out and kept in the backing store, and then we will give chance for P3 to execute. So P3 will now execute. That means P3 will be loaded into the memory from the queue, and after P3 completes its time quantum of 10 milliseconds of execution, P3 will be swapped out and kept in the backing store. Now, what do we have in the backing store? P1, P2 and P3 are all in the backing store. So when P3 completes its execution, what will happen? We need to give chance for P1 to execute again for its next time quantum of 10 milliseconds. So P1, which is present in the backing store, will be now swapped back to the main memory. So from the backing store, P1 will be swapped back into the main memory again, and again it will get the chance to execute for 10 milliseconds, and then it will be swapped out again, then P2 will get the chance, and so on and so forth. So we see in the case of round robin scheduling algorithm how this swapping is necessary and how swapping actually works. So it is just a process of swapping processes in and out of the main memory to a backing store. Alright, so here we can explain with a diagram about swapping of two processes using a disk as a backing store. So here we see the main memory is present. On top there is the operating system, and here is a user space where the user processes can be executed. So this is our main memory, and here we have the backing store that we have been talking about. So as I told you, backing store is like a temporary memory location where the processes can be kept once they are swapped out of the main memory. So here we are saying that we are using a disk as a backing store. So this is a disk which is a secondary memory that it uses the backing store. But remember that though this is a disk, this is a kind of a fast memory that has to be used, because the swapping has to happen quickly. So if we are using a storage that is not fast enough, then we will be wasting time in swapping. So remember that this backing store has to be a fast storage location. So here we are using this disk as the backing store, and as you see in this diagram, there are two processes, P1 and P2. So let's say that P1 was executing, and now we need to give chance for P2. So assuming that this is a round robin scheduling algorithm, what will happen? After the time quantum expires, we will swap out process P1. So once it is swapped out, it is kept in the backing store, and then we will be giving the chance for the other process, which is P2, which was, let's say, swapped out earlier and was kept in the backing store. So this P2 will now be given chance to execute, so it will be swapped into the main memory and it will be allowed to execute. So this is a diagram that just shows in brief how the swapping of two processes take place using a disk as a backing store. Okay, so now let us discuss about the memory space when swapping happens. So normally a process that is swapped out will be swapped back into the same memory space it occupied previously. So in normal condition, what happens is whenever a process is swapped out of the memory location into the backing store, and later when it has to be swapped back into the main memory, then that process will be occupying the same space that it occupied earlier. So for example, let's look at this diagram. So for example, let's say that there is a memory location here where P1 was present. So P1 was executing in this memory location. Let's say that the location is called L1. Now P1 is swapped out and P2 is swapped in. Now later on, P1 has to be swapped in again. Now when P1 is swapped in again, in normal condition, it will try to occupy the same memory location that it was initially occupying before it was swapped out. That is the location L1. So that is what happens in normal scenario. But this is not always the case. It depends on the address binding method. So we have discussed already about the different address binding methods that we have. So this memory space that a process will occupy once it is swapped back into the main memory will depend upon the address binding methods that we have. So if the binding is done at assembly or load time, the process cannot be easily moved to a different location. So if the binding is done at assembly or load time, so we have studied about this already, binding that is done at assembly time or load time. So if the address binding happens at assembly time or load time, it is not easy to move the process into a different memory location. So it has to try to occupy the same memory location that it was occupying before it was swapped out of the main memory. So this is what happens if the address binding is done at assembly time or load time. Now, if the binding is done at execution time, the process can be swapped into a different memory space because the physical address are computed during execution time. So, unlike this one, if the address binding happens during execution time, then it is easy to swap the process back into a different memory location. It is easy to do that. Why? Because the physical addresses are computed during the execution time. So since the physical addresses are computed during execution time, swapping the process back into main memory to different memory locations is not a difficult thing. So if address binding is done at execution time, the process can be swapped into different memory space. So this is how the memory space depends upon the type of address binding methods that is used. Okay, so now let us talk a little bit about the backing store. So as we already saw in the diagram and as I've already explained, the backing store is kind of a temporary memory where the processes will be stored once they are swapped out of memory. As we said, the swapping requires a backing store, and as I already told you, it is commonly a fast disk. It has to be a fast disk because we don't want to waste time in swapping. So this backing store must be large enough to accommodate copies of all memory images for all users. So this is something that is clearly needed because the backing store, it has to be large enough in order to accommodate the copies of all the memory images for all the users. There may be different users that are using the system. So we should make sure that this backing store that is being used, it should be large enough to accommodate all this. Otherwise, the swapping cannot happen. If we are trying to swap something to a backing store, and if that process or that memory image is larger than the backing store, then it will not be able to accommodate that. So in order to avoid that, we have to make sure that it is large enough to accommodate it. And it must provide direct access to these memory images. Only then the swapping can take place between the main memory and the backing store seamlessly. The system maintains a ready queue consisting of all processes whose memory images are on the backing store or in memory and are ready to run. So the system will maintain a queue, and what is this queue? It consists of all the processes whose memory images are on the backing store or in the memory and are ready to run. Then let's see what happens after this. Whenever the CPU scheduler decides to execute a process, it calls the dispatcher. So we see that in that queue, we are having the memory images of all the processes which are on the backing store or in the memory, which are ready to run. They are ready to run. So from these processes that are ready to run, the CPU scheduler will pick a process that has to be executed. So when it picks a process, it will call the dispatcher. So what does the dispatcher do? The dispatcher checks to see whether the next process in the queue is in memory. So it will check if that process that is picked by the CPU scheduler is already present in memory or not. So if it is already present in memory, then well and good, it can just execute it. And if it is not present, what happens? If not, and if there is no free memory region, the dispatcher swaps out a process currently in memory and swaps in the desired process. So if that process that is picked by the CPU scheduler is not present in memory, the dispatcher will see if there is free memory in the main memory or not, because we are going to load a process to the main memory for execution now. So we have to make sure that there is enough space in main memory for that process to execute. So the dispatcher will check if there is space in memory or not. So if there is no space, what it has to do, it has to swap out some process that is present in that main memory, and then it has to swap in that process that the CPU scheduler has picked so that it can use that memory space and do its execution. So as I said, it then reloads register and transfers control to the selected process. That means the process is loaded and it is being executed. So this is how the backing store works, and this is how the CPU scheduler picks a process, and with the help of dispatcher, it will check for that process, it will swap out a process if required, and load the process that has to be executed and will help in its execution. So this was the main thing about swapping, and we have also seen how swapping works, and we have also seen the memory spaces that are occupied during swapping, and we have also discussed about the backing store, and we have also seen how the CPU scheduler and dispatcher takes care of executing the processes. So I hope this lecture about swapping was clear to you. Thank you for watching, and see you in the next one. previous lecture we have discussed about swapping and we have seen how swapping works. So in this lecture we'll be discussing about swap time. So swap time is nothing but the time that is taken for swapping. So we will see how is swap time calculated and what are the factors that affect swap time. So here it says the context switch time in a swapping system is fairly high. So the context switch time that is taken for swapping in a system is fairly high. So we will demonstrate it by taking an example here. So for example, let there be a user process with size equal to 10 MB and the transfer rate of a backing store equal to 40 MB per second. So here we are assuming a user process and the size of that process is 10 megabytes. And then we are also assuming a backing store here. So what is a backing store? We have already discussed in the previous lecture. So backing store is the place where the processes will be kept once they are swapped out of the main memory. So there is a backing store here and the transfer rate of this backing store is 40 megabytes per second. That means the speed at which this backing store can transfer data is 40 megabytes per second. So the actual transfer of the 10 megabytes process to or from main memory takes how much time? Let's calculate. So here we are going to see what is the actual transfer time that is going to take for transferring this 10 MB process to or from the memory. To or from memory means this process can be in memory and it can be swapped out of the main memory into the backing store. So when it is swapped out of the memory to the backing store, it has to be written into the backing store. So the transfer rate of backing store will be a factor there. And then when the time comes when this process has to be swapped back to the main memory from the backing store, again from the backing store it has to be transferred to the main memory. So there also the transfer rate of the backing store is a factor that we have to take into account. So let's see. So here we are going to calculate the time it is going to take. So here our process is of 10 MB, so we are converting it into KB. So 10 MB, if we multiply it by 1000, it becomes 10,000 KB. So we know that actually 1 MB is equal to 1024 KB, that is the exact number. But here we are just doing a rough estimation, so we will be just taking it as 1000. Okay, so 10 MB is equal to 10,000 KB, and what is the transfer rate? 40 MB per second. So if we convert this to KB, 40 into 1000 is 40,000 KB per second. So the time that it is going to take is the size of the process divided by the transfer rate of the backing store. So if we divide these two, what we get? We get 1/4 of a second, which is equal to 250 milliseconds. So this is the actual time that takes for transferring the 10 MB process to or from the memory. So here we see whether we are transferring this process from the backing store to the main memory or from the main memory to the backing store. The factors that affect are the size of the process and mostly the transfer rate of the backing store. So in the previous lecture I have mentioned that the backing store has to be a fast storage. So that is what we are demonstrating here now. So we see that depending upon the transfer rate, the time taken will increase or decrease. So if this backing store had a faster transfer rate, then this time would have reduced. Okay, so for our example, this is the time it takes, 250 milliseconds. Alright, but this is not the final time that it is going to take. We need to take into account some more things. Let's see what they are. So assuming that no head seeks are necessary and assuming an average latency of 8 milliseconds, the swap time is 258 milliseconds. So we are assuming that no head seeks are necessary and we are assuming that there is an average delay or an average latency of 8 milliseconds. So we are just keeping this, which could be the average delay that is going to be there in the system anyhow. So taking that as approximately 8 milliseconds, the swap time will be 250 milliseconds plus this average latency of 8 milliseconds, which gives us 258 milliseconds. So remember that this time that we are mentioning here, it is for the one-side transfer. So since we must both swap out and swap in, the total swap time is 258 into 2, which is 516 milliseconds. So we know that we have to swap the process out of the main memory to the backing store and also from the backing store back to the main memory. So there are 2 times the transfer that is happening. So for one time, for one side, we have calculated it to be 258. So when we are swapping out and swapping in, we have to take into account both the times. So that is why we we are multiplying 258 into 2. So for swapping in and swapping out, the total swap time that is taken is 516 milliseconds. So that is why we said the context switching time in a swapping system is fairly high. So this 560 milliseconds may look like a very small time for us humans, but when computation is done, this 516 milliseconds could be a big amount of time. Alright, so this is how we can approximately calculate the swap time. So as we said, for that particular example that we took, the total swap time is 516 milliseconds. Now, for efficient CPU utilization, we want the execution time for each process to be long relative to the swap time. So for efficient CPU utilization, we need to make sure about one thing. And what is that? We see that the swap time is 516 milliseconds. So we should make sure that the execution time for each process should be relatively long as compared to the swap time. So the execution time of a process that we are giving, that means the time that we are allowing a process to execute in the main memory, should be longer than the swap time. Otherwise, our CPU utilization is not going to be efficient. So here, if we are having a swap time of 516 milliseconds, the execution time, that is the time actually spent by processes for execution, should be definitely more than 516 milliseconds. For example, in a round-robin scheduling algorithm, the time quantum should be substantially larger than 0.516 seconds. So in round-robin scheduling, like we have discussed in the previous lecture, we know that there is a specific time quantum that we are giving for processes to execute. So each processes are allowed to execute for that particular time quantum, after which it will be swapped out and the next process will be given the chance to execute. So here we have seen that in our example, for swapping out and swapping in of a particular process, it already takes 516 milliseconds, or which is equal to 0.516 seconds. So the time quantum that we are allowing a process to execute in this round-robin scheduling algorithm must be substantially larger than the swap time which we have, which is 0.516 seconds. So this is something we have to be sure about and make sure that this is implemented in order to have the efficient CPU utilization. Alright, so we have seen that the major part of the swap time is transfer time. So in the example that we took in the previous slide, we have seen that the majority of the time that is contributing to the swap time is the transfer time. That is the time that is taken for transferring the process from the memory to the backing store or from the backing store to the memory. So the total transfer time is directly proportional to the amount of memory swapped. So the transfer time is directly proportional to the amount of memory that is swapped. Alright, so this is how we can calculate swapping time, and these are the things we need to keep in mind when we design our scheduling algorithms in order to make efficient utilization of our CPU. So now here we will see a few other factors that affect swapping. So let's see what they are. So here it says a process must be completely idle in order to be swapped. So this is something very important. So when a process will be swapped from the main memory to the backing store, we have to make sure that that process is completely idle. That means only when the process is not executing or when the process is not being accessed by anything else, only at that time it can be swapped. So when a process is executing in main memory, when it has to be swapped, that process has to be stopped. It has to be halted for the time being, and only after making sure that it is completely idle, then only we can swap it. So a process may be waiting for an IO operation when we want to swap that process to free up memory. So let's think of a scenario here where we are trying to swap out a process from the main memory. But during that time, when we are trying to swap that process out of main memory, at that particular time, that process may be waiting for an input-output operation to be performed. So will we be able to swap that process out at that time? No. If the input-output is asynchronously accessing the user memory for the input-output buffers, then the process cannot be swapped. So when we are trying to swap a process, and if that process is being accessed by the input-output operations, then we will not be able to swap that process. So that is why we say a process must be completely idle in order to be swapped. So by completely idle, keep in mind a process should be halted from its execution, and also that process should not be waiting for something at that time, especially input-output operations. So if that process is trying to wait for or access some input-output operations, then at that time that process cannot be swapped. So these are some other factors that we need to keep in mind which affect swapping. So I hope this lecture about swapping time is clear to you. So we have discussed about how to approximately calculate the swap time. Then what are the things that we need to keep in mind while designing a CPU scheduling algorithm based on the swap time that we have. And we also saw some of the factors that affect swapping. So I hope this lecture about swap time and all these topics that we have discussed is clear to you. Thank you for watching and see you in the next one.